Might as well introduce him now. Joe is one of the several dozen folks eventually that comprised the attitude control function that was programmed into the computer. And Joe is a key person in terms of understanding this barbecue mode that you've been analyzing in the last problem set or two. How's the sound? You okay? Good. Yeah, the title of the talk is Some Dynamics and Control Challenges That Occurred During the Apollo Project. And there were lots, but I'll try to limit it to what can be said in 50 minutes. The space race started more than 10 years ago when Sputnik was put up in 1957. We had the 50th anniversary of that recently. And the Russians were ahead of us for most of the early years. And Kennedy finally said in exasperation to his advisors, well, what can we do and be first? And they came up with the idea we can probably beat them to the moon and back. And so Kennedy announced in the early 60s that this nation was committed to sending a crew of astronauts to the moon, landing them, bringing them back safely to Earth. And so that was the culmination of this space race. We thought we could beat the Russians at doing that. So the concept was to use, the thing that I'll talk about and that you are familiar with from your problem set is this configuration of the spacecraft which got launched out of a parking orbit in Earth orbit and injected on an escape velocity to go to the moon and back. So I'll be talking about this configuration in the barbecue mode, and I'll also be talking about this configuration in a backup mode that was extraordinarily important in Apollo 13 to saving the lives of the astronauts when the service module exploded and they had to use the lunar module to push the crew back to Earth. The concept of how to launch in a single launch from Cape Canaveral this whole stack within the existing technology, John Hubble of Langley said, lunar orbit rendezvous is the way to have the least liftoff mass coming off of the Earth. So the concept was big Saturn V pushes the whole stack into Earth orbit. You check out the systems for a while, and then you, with the last stage of the Saturn, you go into an escape velocity trajectory, free return trajectory. Is there a pointer? I don't want to stand in front of this. Should have had a laser. Well, okay. So free return trajectory in case something went wrong going around the backside of the moon. Come on back. After, if everything's successful, do the lunar operations in Earth orbit with the lunar module going down, coming back up from the surface, rendezvousing with the mothership, trans-Earth injection back to Earth, separate everything except the conical capsule, do a fire re-entry into the atmosphere, deploy the parachutes, and drop to a target point near some ships.
I'm supposed to call.
10:10 already?
Yes.
Holy smokes. I asked Sheila to ring the bell because I could go on forever on any one of these subtopics. Okay, so so all the functionality needed to take this spaceship to the moon and back and to take the LEM down to the lunar surface and back was contained in what was then first-time computer controlling things. This was an example of the memory stack involved. This had 74 kilobytes of memory. You guys know that this thing has 2 gigabytes of memory in it. So this kind of memory stacked up, a central processor that could only clock at about 1 million times slower than a typical Pentium, 6 orders of magnitude difference in speed. I mean, this was really primitive. So this was the first time that such a computer was going to be used to directly control an aircraft or a spacecraft. The mission sequence, and there was obviously an orderly sequence building up to having the courage to go down to the moon and back. And the flights that I'll talk about most in this orderly sequence was, well, Apollo 8 is famous. I won't talk about it too much, but 40 years ago, before Christmas, that's the first time the men went out around the moon and sent back those glorious pictures of Earth rising over the lunar surface. And that was kind of the start of the environmental movement. Fragile spaceship Earth. But we'll talk about Apollo 9, the first time the lunar module was in Earth orbit, being tested with people on board, testing out rendezvous and so on in Earth orbit. We'll talk about 10, The first time a full-up spacecraft was launched on the off to the moon, and that's where the barbecue mode and its problems was discovered. That was 40 years ago next spring, and then we'll sort of backtrack to getting ready for this one. What did we put into the computer program to be able to carry out this LEM operations in Earth orbit successfully, and what was used in Apollo 13? It was just essential that it be there. Okay, the barbecue mode, which was that first time the all-up spacecraft was launched to go out to the moon, but not do a landing. And to keep the thing from getting unevenly heated, once it was boosted out of Earth orbit, it was supposed to be put into this very slow rotation. And the idea was to spin this thing up very slowly, you know, 1 revolution per 10 minutes or 20 minutes, but constrain it to be rotating about the geometric roll axis without regard to where the principal axis might actually have been. So this was initiated to spin this thing up and hold it close to that roll axis as the axis of rotation. And there was a problem. The jets kept firing, and they never were satisfied. And we came to the understanding that, of course, what was going on was that because of this being the light axis and these being the heavy axes of rotation, and the principal axis not being aligned here, the angular momentum vector was noticeably away from this desired angular velocity vector. And so it was going to require this amount of continuous torquing to force that angular momentum vector to be coning around in space in order to keep the angular velocity vector in the direction that had been chosen for the barbecue mode. Unacceptable. So then the suggestion came, now this is in real time. The astronauts couldn't sleep. And we unfortunately hadn't simulated this in our computer. We hadn't really checked this out and would have discovered this problem because we had all these inertias and so forth. So this was news to us that this wasn't going to work very well. And so in real time, we said, well, what to try? Well, after you've spun it up, maybe just turn the jets off.
Yeah, I don't think you've talked enough about the fact that the jets were being pulsed.
Yeah.
And you guys did that on your homework, right? It was like once a minute or once every whatever you got in your homework.
To deliver this average level of torque that was required to keep the angular momentum coating around, the jets only could be turned on and off, so you had to pulse them. Pulse, pulse, pulse. So on a time average basis, you would deliver that average torque that was required. And these are the jets here that would have to be fired, these little quads of clusters of 4 jets, so boom, boom. So the astronauts were hearing this bang, bang on the oil can, and they weren't getting any sleep. And they've got a 2-day trip to the moon going on. And so what to do about it? Well, the first idea was, well, just disable the jets. Don't let them fire. And this thing will probably happily keep spinning around somewhere near where it was initiated. Well, it doesn't. It does not stay very close. And you folks have done some computations on what happens, and we repeated, Sheila and I repeated these calculations, and Joe later did also after the actual flight, to see what the motion was going to be if you turned those jets off. You have to integrate 3 Euler angle equations to keep track of the attitude of the spacecraft, and you have to integrate 3 angular velocity equations to keep track of the angular velocity. So you have 6 first-order differential equations that have to be integrated to see what the motion's going to be. And this is the inertia tensor in body axes, not principal axes. And so in the first case that we simulated, the initial conditions were set all the Euler angles to 0, 0 roll, pitch, and yaw angles, and start with 0 pitch rate, yaw rate, and a very, very small roll rate equal to 1 revolution per we used 10 minutes. Joe later used 20 minutes in the simulation he did 40 years ago. But for the purpose of this lecture, we did 1 revolution per 10 minutes. Case 2, which I'll come to later, is the one where you spin it up about the, well, I'll talk about that later. So here's the initial thing. What would happen if you spun it up around the x-axis, then turned the jets off? What would the subsequent motion be? And integrating these 6 first-order equations that are coupled gives the answer to that question. And the answer is that for that inertia tensor and so forth, that the azimuth and elevation of the spacecraft, starting at 0 azimuth error and 0 elevation error, versus time, is that plot there. And this plot is plotting azimuth and elevation on the same plot. So you can sort of track what the motion is of the nose of the spacecraft as it's going around. And you can see that by these blips here, if you count them, you can see that it's basically doing 1 revolution per 10 minutes or so. But anyhow, that's a detail. So what's going on here? What's this motion all about? This funny behavior of the x-axis. It's a little bit like, I like to think of it as a little bit like watching somebody on a bicycle, you know, looking at their front wheel. And if you look at the axle of the wheel, it seems to be a nice uniform motion going around. But if you concentrate on a drop of paint on the wheel or the valve where you put the air in, the motion that you see is something like this. And this wheel is rolling along without slip. Okay? Remember, body cone on space cone without slip. So that's the kind of motion you get if you don't set up your coordinate system to concentrate on something more fundamental. And that's what you're looking at here. You're looking at the motion of the x-geometric axis bouncing along like that bicycle, perimeter of the bicycle wheel, when something more fundamental is going on than this thing that happens to be the x-axis of the spacecraft. And the free motion would have gone as far away from where you started as maybe 30 degrees. That would have been okay for the barbecue mode, probably, but it was very risky, and we didn't know then how far it would go. I mean, we're talking about in the first half hour or so, it's going like this, and we didn't really have the dynamic model in our head of what was ultimately going to go on, that it was going to come back. And you didn't dare let these angles get out near 90 degrees because perhaps Professor Dice talked about the problems with a 3 gimbal angle inertial measurement unit. If you get out near 90 degrees, you get in a condition called gimbal lock, where you're now putting in jeopardy the integrity of the gyroscopes. So we were always very worried about gimbal lock, and so this was unacceptable. And so the jets were turned back on, they're banging away, and MIT's got this hotline down to Houston, and they're calling us to say, what do we try next? What's next? And that's when I had the insight that the problem was that the angular momentum vector from that initial condition was somewhere off here, 10 degrees or so away from that initial angular velocity. And if we wanted to have a more constrained motion with the jets turned off, then we had to somehow get that angular momentum vector initialized much closer to the direction that we wanted to point. And so, so I came up with the idea that, well, look, instead of forcing an angular velocity as an initial condition, how about forcing an initial angular momentum as an initial condition? And the way to do that, since the time rate of change of angular momentum is torque, is to apply a torque and let that angular momentum develop along that torque. And in spacecraft axes, the astronaut had the ability with his rotational hand controller to put the autopilot, take it out of the automatic attitude control mode, and just go into free flight, and with his rotational hand controller call for a little minimum impulse, around the roll axis, and another minimum impulse, until he built it up to this 1 revolution per 10 minutes or 1 revolution per 6. Pure torque about the x-roll axis. And that then led to the angular momentum vector being along that axis, except for the fact that there were some residual low-level pitch and roll rates that you couldn't easily null out at these low levels. So they, down in Houston, they said, you're telling us to turn off the control system after these large excursions that we saw, to turn it off? And we said, try it, you'll like it, you'll like it. And, and so they radioed up to the astronauts the instructions. Okay, shut down the automatic attitude control. Let's quiet the spacecraft down to as steady a flight as possible. And then with your rotational controller, just give it a little torque until you're up to speed. And you know from your problem sets what the difference is between those two situations. With that initialization, and I'll come back to the idealized two inertias equal case, but with that initialization, you have a motion that that now has its angular momentum vector right there along that x-axis where you applied that torque to spin it up, and you get this looping motion, because the x-axis isn't really the fundamental thing to track. But the maximum excursion is now of the order of a few degrees rather than 20 or 30 degrees. So this was a wholly acceptable motion to torque it up, then shut all the jets off, and get a good night's sleep. Now, let me come back to, and we didn't fully understand what we did, how great the reduction in amplitude would be and so on. But as we reflected on it after the flight, I mean, this was kind of real-time reacting, trying to help the astronauts get a good night's sleep and avoid gimbal lock. Oh, and one other slide in terms of the kind of motion. Well, one other slide, again, showing the difference between what you get integrating the differential equations with one initial condition, what do you get with the other initial condition. This is the motion from just applying pure torque to get the angular momentum vector there, and this is the motion that we got when we applied an initial angular velocity, and which put the angular momentum vector over here. So a huge reduction in the size of the free body motion. Okay, and then when we got to thinking about it afterwards, what was this all about? And now you get into wanting to remember, be aware of, and wanting to remember this beautiful, elegant solution from classical rigid body dynamics on the motion you get if two of the principal axes are equal. Now, they were nearly equal in this case, not quite, but they were nearly equal. So the insights from this elegant thing are really strong. In the case, two principal axes equal. In the case where you spin it up for this initial angular velocity, and as you're spinning it up to the rate you want, you wind up with an angular momentum vector over here, 11 degrees away. You turn off the active torquing and see what the free body motion is going to be. We had a principal axis that was less than 2 degrees away from that spin axis. Turn the jets off. Now you've got this beautiful classical space cone separating, fixed in space, on which this body cone is rolling without slip, going around, going around, going around. So this point here on the body cone is doing this bicyclist wheel kind of thing if you track that initial point on the x-axis of the spacecraft. So beautiful, elegant solution, a way to visualize and remember what's happening in this kind of situation. And the other solution for the other initial condition, setting, assuming the two principal axes are equal. Where'd you go, friend? Just a moment. Oh, here it is, in the black of night. Yeah, the other solution, has this kind of relationship between the space cone and the body cone. The one where we applied a pure torque and got the angular momentum vector aligned along the desired axis for the barbecue mode and then turned the jets off, gave rise to an initial angular velocity that was not too far away, less than 2 degrees away from the initial angular momentum vector. And that angular momentum vector was going to be a constant in space. This initial angular velocity, instantaneous angular velocity, was the point of contact between the space cone and the body cone. So the body cone's only 1/10 of a degree or so in half diameter. And the motion is going to be that of the body cone rolling without slip around the space cone. And the thing that we're tracking in that picture of the looping bicycle is we're not tracking the motion of the principal axis, which is very smooth, but we're tracking this point on the x-axis of the vehicle. And what is that point on the x-axis of the vehicle? What's it going to be doing? Well, it's sort of like a big disc on top of this small cone, so it's going to be looping around, coming back and touching zero angular momentum from time to time. And that's indeed what you saw on that other slide. So that was pretty exciting. And Joe ran these simulations in the month or two after the flight. The numerical integration of the exact differential equations with unequal principal axes. And he got those results that confirmed, okay, this is what happened, this was what's going on. He never published that as a full paper in the literature, but he did document it as an internal Draper Lab memo, and that's sort of a classic. I've got a copy of it. That was a good one. Okay, so that was what the barbecue was all about, and the astronaut said, thank you very much. Okay, now the other topic I wanted to talk about, how are we doing on time, Sheila? Okay. Was there something more you wanted me to say about this? Because this is central to your course. Yeah, that's good.
I mean, having shown the space cone and the body cone, you might put the numerical thing back up again to show the relative sizes of the motions as we actually calculated using the non-equal moments of inertia.
Yeah.
Because it kind of reflects that. Size of the space cone and body cone in the two problems, and now you see the exact solution in the two problems. You can see their relative sizes.
The initial angular velocity for the exact numerical integration with the unequal principal axes, you got a motion with the angular momentum vector 11.4 degrees away. And I'm sorry, here. This is the exact numerical integration, and you see that the angular momentum vector is somewhere in here. The theory for equal inertias, if you sort of average those two inertias and use that, says that cone would have been 11.4 degrees away. So that this elegant solution very well predicts what the actual equations would say. The looping motion predicted by the numerical integration has that initial angular velocity that was right there at 0, 0, elevation and azimuth, looping back to some surface that seems to be, well, it's looping back to some surface that's maybe 11 degrees away from whatever. But suffice to say that the elegant classical solution provides tremendous insight and good numerical results for what the actual numerical integration shows. And similarly for the other case, that it's well predicted that the motion will keep coming back and touching the origin in elevation and azimuth, as is seen in this diagram here.
Yeah, I guess the only other thing I'd mention is that there would be a real danger in allowing the Apollo spacecraft to start rotating around that long axis because there's that kinetic energy instability?
We did recognize, we were aware of,
NASA was worried about that.
yeah. As to what the time constant of that decay would be, I don't know. We didn't know. It is a known fact that for a given amount of angular momentum, the rotation that has the least energy is not the roll around the light axis, it's a tumbling around the heavy axis, same amount of energy. But how quickly do you decay from that to that? That depends on how much damping there is in the fuel that's sloshing in the tanks, how much the astronauts are bumping into a wall and dissipating energy in that way. So we had no idea what the energy dissipation rate would be, or so how quickly it would go from this to this. So we weren't too worried about it. We thought, and especially where the initial barbecue mode design was to constrain it by actively firing jets to stay along that unstable axis. So, okay? The other thing I wanted to talk about that had some dynamics in it and a lot of emotion in it was, so what we were talking about here was Apollo 10. Apollo 10? This is the first time the command module and lunar module and a full crew of 3 went out for a voyage to the moon and back, then the sleep problem. That was Apollo 10. Now, Apollo 13, there was a big problem. Back up before Apollo 10 to Apollo 9? 9, I think it was. Yeah, 9. Rusty Schweikert, McDivitt, and Scott. First manned lunar Earth orbital, first manned LEM in Earth orbit. So Apollo 9 was the first time that the LEM was in orbit and a crew was going to get in it, and they were going to detach and practice rendezvous and coming back and so doing this all close to Earth. Now, an earlier flight had failed. There was a flight that every now and then there was a failure. One failure early killed 3 people. I mean, this is a pretty risky endeavor here. But a failure of significance to developing the propulsion systems and the guidance, navigation, and control equations was this unmanned flight Apollo 5 last January, so to speak, 40 years ago today. And that flight was going to send an unmanned lunar module up into Earth orbit. They were going to test the throttleable descent engine. This engine, which is pretty new technology, could put out 10,000 pounds of thrust, or you could throttle it down to 1,000 or 2,000 pounds of thrust. So needless to say, they wanted to test whether or not this throttleable engine would work, not blow up and do other things. So they planned to do that without any people on board. That mission failed. I don't remember why it failed, whether it didn't even get into Earth orbit or what, but it failed. So now they have to load onto a subsequent mission if they're going to stay on Kennedy's schedule. They have to load that propulsion test onto a later flight. So they loaded it onto Apollo 9. Now they're going to be men on board and astronauts on board, and they're going to test the throttleable engine and this and that. So when this requirement, meanwhile, we've been thinking about what can you do with that lunar module engine? We've done some preliminary thinking about it. You could actually control the spacecraft from the lunar module if you had to. But NASA laid down a requirement after that failure that we got to have a way to test that engine in Earth orbit that doesn't, for a long burn, such as landing on the moon, without having the LEM go scooting off somewhere in some other unreachable orbit, and how do you rescue them if there's an explosion or whatever. So they wanted to come up with the ability to test that throttleable engine without going anywhere, staying attached to the mother ship in case there was a problem. And so how is this going to happen? How are you going to be able to, with the little thrusters on the lunar module and its main engine, which was barely gimbalable, how are you going to be able to control this much heavier configuration? The LEM wasn't designed to do that. And but but I had an idea on how it could be done, and the key was to let's see, the next slide I'd like to show you is yeah, here we go. Okay. So again, this just shows some of the capability of the lunar module. It had a very light ascent stage with a fixed propulsion engine that brought it back up to the mothership on a lunar mission. But for descending to the lunar surface, here's this descent engine that is throttleable, and in addition, it has a very slow gimbaling capability. It can be, in case you didn't luck out and have that thrust go right through the center of mass, you were going to have a biased torque, and then these little jets were going to have to pulse to keep things on track. So this descent engine had a capability with a worm gear that could gimbal it very slowly, 0.2 of a degree per second. So sort of like 2 seconds to go the width of the moon, you know. Moon's half a degree across. So 2 seconds to go across the moon one way, 2 seconds across the other. Very slow gimbal capability. Just meant to trim out the bias torque so that these little 100-pound, 400-Newton thrusters could do the job of attitude control with their occasional pulsing. So I said, well, you know, maybe that 0.2 of a degree per second gimbaling rate is fast enough to control the big configuration. And one motivation for wanting to do it was well, the control authority, these little jets over the big configuration, wasn't going to be that great. And a lot of propellant was going to be expended, so what could be done? Well, if this is docked to the lunar module, you had to start worrying about some other things. First of all, you couldn't be exhausting into the astronauts' faces in the command module. That wasn't any good. And when you exhausted down, there were these splash guards here that kept the exhaust from ripping up the gold foil that was providing thermal protection on this stage here. And that deflection of the thrust put an adverse force on here, which is a torque in the wrong direction if the center of mass is up there. So move the center of mass from here, where you don't care so much about that, move it way up there, and you got to worry about just trying to torque this way, get what you want, or does you actually wind up going the wrong way? So there are a lot of reasons to be very concerned about the ability of the lunar module to control that. So another one in the dark zone. Okay, so here's the challenge. Here is the challenge. With the problems of the impingement of the exhaust and this and that, I wanted to see if there was some way to use this gimbalable main engine, center of gravity way up here, just slowly slewing that back and forth to while the main descent engine is firing and pushing this whole configuration, to actually steer it while it's firing, just using this gimbaled descent engine and hopefully not even using any of the attitude control jet's fuel. And about that time, a field in control theory, that was then called modern control theory, had to do with optimal control. It was based on some early work by the Russians, surprisingly enough. There's a space race against the Russians. But Pontryagin and Gomkrolitsy and others, the academicians in Russia, had come up with this very elegant mathematical theory of time optimal control, fuel optimal control, which involved bang-bang controlling. And an example of a minimum time controller is if there's a traffic light here and a traffic light here, and you're going to drag race somebody from when the light turns green on the drag course from here to here, what's the minimum time to get from there to there? Well, it's to hit the accelerator as hard as you can until you get to where you think if you hit the brakes you won't hit the wall, but you'll stop right there. And so the control action involves accelerating as hard as you can until you get to the point where you hit the brakes and decelerate as hard as you can and come to a stop right there. That's the minimum time way to get from here to here. It's a bang-bang controller. It's always using the maximum amount of force that's available to you. And in the case of the so-called double integral plant, this is an F equals ma problem where you're controlling distance to go and velocity using acceleration as the control variable. So it's a so-called double integral plant, and the optimal solution for that is 2 periods of constancy of the control will get you there. And so this is intuitively a well-known example of time optimal, minimum time to get from here to here. Well, I said, well, let's find the minimum time controller to control any initial condition in this configuration. But this was a third-order plant. This is third order. We've got the control variable in this case is not angular acceleration. Now we're doing rotational control. We're trying to control the deviation in angle from the direction we want to thrust. We're trying to control the angular velocity around that pitch axis. But the control variable isn't instantaneously applied torque. The control variable is the rate of change of the gimbal angle. So you got one more integral in there. You got to be driving the gimbal angle, and the integral of that gives you the angle, which gives you the torque, which controls the other two state variables. So this is a third order plant where the control variable is delta dot at 0.2 of a degree per second. So again, we're looking at now not the double integral plant of drag racing, but we're looking at the triple integral plant of using this maximum on worm gear drive to build up an angular acceleration, which then controls the angular velocity, which then controls the angle. So we want a control law that looks at these 3 state variables and decides at each point in time what the best action is, which way we should be driving that thrusting engine. This problem had not been solved, so Athens had just published a book. MIT professor Athens had looked at the translation of the Russian work and was starting to offer a course at MIT in an optimal control theory. And he later published a book, and he put in as a problem for the student to extend these ideas to third order. And he said, show that this is so. Well, what he had you show was wrong. So although Athens said, I think these methods can solve that problem, his solution was not right. So I credit myself with being the first one to get it right. And so the control law, the characteristics of the optimal control law, remember this one is hit the accelerator, hit the brakes, 2 periods of constancy to control 2 state variables. The optimal control law in this third order problem is 3 periods of maximum drive on that gimbal angle, on that engine angle rate, which will take any initial offset, any initial condition of the 3 state variables, bring it to 0 in minimum time. And the particular one that was going to be of interest was not being able to align that engine perfectly through the center of mass at ignition. There was going to be a misalignment. The attitude error would be 0, the rate would be 0, but there'd be this misalignment. So you'd get from that initial misalignment an angular acceleration, which had to be brought down, and the resulting rate and angle excursion, those two had to be brought back to 0. So it's accomplished by 3 periods of constancy, which brings down that initial misalignment, goes in the other direction to stop the growth of angular velocity, does what's needed to turn around the attitude error, and now bring them all back to 0 in the minimum time. And for some of the numbers that we worked, the various levels of control effectiveness or so on, if this was the level of the initial misalignment, it was going to take something like 9 seconds to capture that initial state error and slowly bring the spacecraft back to right on 0 attitude error, 0 rate error, and 0 bias torque. So that was going to be the nature of the solution according to the theory. And so we programmed it up for this computer. And the computer, with a cycle rate that was 1,000,000 times slower than a Pentium, the fastest that you could recompute the optimal control law was like every 200 milliseconds, like 5 times a second. You could reevaluate, am I on the right track? Should I change my control strategy, and so on. but that was good enough to be able to reevaluate this every 5 seconds, and keep the thing on track. So we programmed it up, and we tested it in the simulation because there were a lot of things that weren't in the theory. The effective sampling time wasn't in the theory. The bending mode, possible oscillations, wasn't in the theory. The fuel slosh confusion. So all this stuff had to be modeled in the dynamic simulation that we used to check out the proposed onboard computer programs. And we flew it in that simulation, and sure enough, it flew. The simulation work with all the detailed dynamics in the simulation said, yeah, this will work, this will fly. So the control law that got programmed was, this is the optimal control law. I don't expect you to understand it, but it's a memoryless function of the 3 state variables, bias, angular acceleration, angular velocity, and attitude error. At each point in time that you know that state, this is a memoryless calculation that tells you what the optimal control, which way to be driving that signal. That had to be programmed up. I non-dimensionalized it because we didn't have floating point arithmetic. We're dealing with fixed point arithmetic. And this is the control effectiveness, the thrust of the throttleable engine, the distance to the center of mass, the rate at which the gimbal could be driven, and the moment of inertia of the spacecraft, whether it was this full enormous configuration or whether it was just the LEM itself almost out of fuel descending to the surface. So, I mean, there are huge range in this control effectiveness. So we non-dimensionalized the equations so that they could be programmed within double precision fixed point arithmetic. And it went really well. If you want to see some performance results, both as predicted by the simulation and as proven when they used this in orbit, it's in a paper that I published a year after the first lunar landing, and I think Sheila will have. Did you stick it up on the web? Yeah, we published a paper at a conference. The Russians were attending, and, they were interested in how the hell you make gyroscopes. I didn't know anything about that. They needed John Dice for that one. But anyway, I did publish this paper in Automatica, and it credited the Russian academicians for the theoretical work that this was based on. But in that paper, you'll see a comparison of the performance that the simulation was predicting and the actual telemetry that came down from the flight test in Earth orbit of that descent engine and so forth. And so that was entirely successful. Then it turned out to be very fortuitous that we had this capability in the lunar module computer, because later, after the first successful lunar landing, which was Apollo 11 come next July 40 years ago, there was a sequence of missions that went to the moon and landed and came back. And there was, after 11, there was 12, and then 13 was sent out, and they had some bad luck. The side of the service module blew out on the way to the moon, and it incapacitated the command module and service module. And now free return trajectory looked pretty good. That was fortuitous, that the mission planning had a free return trajectory. So if everything went okay, you could loop around the moon and come back. But there was the question of how are you going to do these mid-course corrections? You know, when your navigation said, no, you're not hitting the right entry point at the right angle into the atmosphere. So you have to do a mid-course correction to keep targeting for the right kind of entry conditions in the atmosphere. And for that, we used the lunar module pushing the command service module. And there were many engineers working day and night to try and figure out how to save those astronauts. And the MIT folks were part of those people that were being consulted. And this capability that we put in the computer to use the LEM to push the command service module was one of the key things that made it possible to get them back alive. So that was very, very emotional. And we're very proud of what our team here at MIT Draper Lab were able to do. So that ends my remarks. If you have any questions, I would be delighted to try and answer them. Joe, any comments?
It was a wonderful time to be involved with a project. It was a once-in-a-lifetime opportunity.
Indeed it was. I was a very lucky young engineer. I mean, I hope all of you have this kind of luck some point in your career, but I mean, I had decided to shift from where I had done my master's in the electrical engineering department over into Aero and Astro to do my doctorate. And well, at first and so I became a research assistant in the Aero department, Aero Astro department, and close connection between the academic department and Doc Draper's instrumentation lab, as it was called then. Doc was both department head and head of this laboratory, which is now named in his name in honor of him, Draper Lab. So here I am doing a research assistantship on this Apollo work that's starting up. And it was during that time that I was a research assistant, I think, that I did the solution to the triple integral plant. So that's one hell of a research assistantship opportunity. Just luck. I mean, the MIT had this connection with practical applying theoretical knowledge to make things actually happen. MIT was very courageous about taking a principal role in this. They could have failed and had egg on their face. So that was great. That was lucky for me. And so then this thing proceeds on, and I was just part of something. I was in the right place at the right time. So I was very, very fortunate. As Joe said, those of us that had the good fortune to work on this at that time it's very special.
Without luck, we would have been designing washing machine engines at GE.
You folks may not have, there won't be the same sense of urgency on getting a permanent base on the moon and a voyage to Mars. I mean, that'll be an ongoing objective. So you won't, I don't think you're going to see in your lifetime that becoming the big objective. I think for now, saving the planet has got to be a more important objective. So you maybe will have those opportunities in designing wind turbines and geothermal energy systems and extracting energy from the ocean. So, I mean, there's a big priority there, and maybe you'll have the kind of excitement we had in trying to get to the moon and back. You'll maybe have that in your efforts to help save the planet. But there'll be opportunities there, and you'll be very glad that you had an MIT education that gave you these fundamental understandings of these things that will enable you to be on a team where they're really puzzled over, this can't be done, how are we going to do this? And you'll think back on the theoretical underpinnings of what you're trying to do, and you'll say, oh no, this can be done. And you'll have the fun and excitement of having that experience. So thanks very much.